Okay, so in this section, we're going to talk about closed sets. And I know I kind of mentioned the concept of closed sets before when we were talking about subsequential limits. So now we're really going to deal with it in kind of the full, in its full splendor, okay? But you'll see how it ties in, it's, the definitions we make here will be consistent with what we were saying before about closed sets, okay? So let me just state the definition now of a closed set because it's a little bit strange and it's sort of hard to motivate. So I think after I state it, we can look at some examples and hopefully it'll make some more sense. So this is going to be definition 13.8, right? So let SD be a metric space. A subset E is closed if its complement is open. So, i.e., if S, and they use this symbol for set subtraction. Whoops, no, sorry. If S E is open. So just to, in case anyone's unfamiliar, the complement of a set within another set is just the collection of all the points in the larger set which are not in the given set, right? So this symbol here, S\E, is the complement of E. It consists of all the points of S which are not in E, okay? So you're just sort of flipping for every element you're flipping whether it's in the set or not. This is equivalent, so equivalently, E is closed if E equals the complement of an open set. Because remember, or at least maybe if you don't remember, hopefully it's not too hard to see that if you take the complement of E, you get E again. So if we're saying that E is closed when its complement is open, that's the same as saying that E is closed when it is the complement of an open set, right? So if E's complement is open, then it's also the complement of its own complement. So that means it's the complement of an open set, okay? So this is the definition of what it means to be closed. It looks a bit different, right? It already looks different from what I was saying before about, right? For subsequential limits, I was saying the set of subsequential limits is closed because if you take any sequence of points inside of it, the limit of that sequence, if it exists, must also be in the set. It turns out that will be a consequence of this definition. So if we take this as the definition, we can prove that any closed set also has the property that when you take a sequence of points inside of it, the limit of that sequence, if it exists, must also be inside the closed set, okay? So first, so I'm gonna list some of these properties in a bit, but let me just give some examples of, closed and non-closed sets. So let's see. Oh, actually, sorry, this definition isn't finished because there's some related stuff. So before I do that, let me finish stating this. So, right. Yes. Okay. The closure of a set, which we write as E minus with a bar here, or I might sometimes write it with an overline, but I'll try to stick to this. This is the more standard notation, I think. So anyway, the closure is the intersection of all closed sets containing E. Okay. Uh, so right. So this closure, it exists for any set, any subset of S, right? So you can take the closure of any subset of S. It doesn't have to be open. It doesn't have to be closed or anything. This is just, you can make this definition for any set in S. And of course, if E starts off being closed, then taking the closure will end up doing nothing, although you have to actually prove that. But yeah, so, this is a useful thing to be able to talk about. If you're dealing with a set that you have no idea whether it's closed or not, you might be interested in taking the closure of it. So then the last bit here is, so the boundary of E is the set difference of the closure and the interior. Okay. So if you take the closure of a set and then you take away all the points that are interior to the set, you're left with the boundary. All right. So yeah, and the points in here, the points in the boundary are called boundary points of E. Okay, so let me move to a new screen here. So let's look at some examples. Right, so if we take, something like A, B, half open, right? Where B is greater than A, of course, is not closed. Why is it not closed? Because the complement is the union of two intervals. We have negative infinity to A open on this side, union B closed on this side, infinity, right? And so it's this point, the point B is in the complement, and this point B is not interior to the complement, right? So B is not interior to the complement, right? So the complement is not open. So if the complement isn't open, then the set is not closed, right? Okay, so now let's talk about the closure, right? So the closure is going to be, surprise, surprise, the closed interval from A to B. And I'm not going to prove that right now because it's a little bit tedious using the definition that we have. Once we state some of the properties of closed sets and closures, it'll be easier to see why this is the case. But you should think, here's the intuition though. The closure is the intersection of all closed sets containing this. So it ends up being the smallest closed set, quote unquote, the smallest closed set that contains the given set. So it's pretty clear that like, it's hard to get much smaller than, like obviously if you have to contain the half open interval from A to B, this closed interval only differs by adding 1 point, right? So this is probably the smallest closed set that contains this one, right? But so that's the closure. So and the interior, right, of this set is the open interval from A to B, right? These are all interior points because they're strictly in between A and B, so you can draw little bubbles around them that stay within this half open interval. But of course, the point A itself is not interior because it's like right on the edge here. In other words, it's a boundary point, right? So the boundary, sometimes written as this curly D, like a partial derivative. So the boundary of AB, which is the closure minus the interior, right, That's just the set of 2 points on the edges, right? So notice that B is actually not in the original set, but it's still considered a boundary point, okay? So sometimes there are boundary points which are not inside of the original set. Okay, so that's our example. Now let me state some properties of closed sets. So this is proposition 13.9. Properties of closed sets. So the first one here, and these are, I'm not going to prove because it's left as an exercise. It's on the homework. So E is closed. I actually mentioned this one already. If and only if E equals its own closure. So if you take the closure of a closed set and you get the same set back, then if you take the closure of a closed set, you will get the same set back. But if you take the closure of a set and you get the same set back, that means the original set was also closed, which shouldn't be that surprising. So now here's an important one. So the set E is closed if and only if it contains, sorry, this is an if and only if it contains the limits of all sequences of points in E. Okay, so this is the version of the definition that we were talking about before, right? So what I was saying is that it turns out that these definitions are the same, which is maybe not that obvious from the definition that we made. An element is in the closure if and only if it is the limit of a sequence of points from E, and D, a point is in the boundary of E if and only if it belongs to the closure of both E and its complement. A point is in, I'm going to write it this way, the boundary of E. This is the boundary of E. If and only if it is the, sorry, only if it belongs to the closure, if it is in the closure of E and its complement. Okay. So in a sense, being in the closure of a set means being close to the points in a set. So basically being on the boundary means being close to the points in E and also close to the points in the complement of E, right? And what I mean by close is actually exactly this, right? If there's a sequence of points in E approaching another point, that point has to be pretty close to the points in E, right? So that's why the closure kind of consists of all the points which are close to the set. If we go back to our previous example, right, you can see that the point B has to be in the closure of this half open interval because you can take a sequence of points marching from the left, like, B minus 1 over n is a sequence of points in A, B, at least assuming n is big enough, right? Like, so early on, it might not be all within here, but eventually this sequence starts to land in this interval. So it forms a sequence of points in this half open interval converging to B. So B is in the closure by 13.9, okay? So that's kind of the power of this collection of things. This is an important set of exercises for any beginning topology student, is sort of drawing all the connections between the different formulations of openness and closedness, okay? Once you really grasp this, it's extremely powerful. So I think that will be it. The last thing I want to say is I just really want to drive home the point that, like, there are sets which are both open and closed, right? The empty set, I'm also going to write this over here as a side note. S and, oops, S and the empty set are both open and closed. For a metric space, if you're talking about the sets that are open and closed in the metric space S, the whole set S and the empty set are both open and closed, right? Because they're both open, and the complement of S is the empty set, and the complement of the empty set is S, right? So they both have to be closed too. So it's possible to be open and closed at the same time. Sometimes there are more sets which are both open and closed than just S and the empty set. And then also, you know, in R, half open intervals are neither open nor closed. Among other sets, there are lots and lots and lots of sets which are neither open nor closed, okay? So you have to remember that open and closed are not like a binary thing. It's not like a set has to be open or closed, and it's exactly one of those things. It could be one or the other, both or neither. Those are all perfectly possible, okay? So yeah, that's going to do it for this segment. In the next one, I will talk about the Cantor set.